Okay, so this is what we covered last time. So in the first part of the talk, we spoke about how computer vision research has been understanding images several years ago. And the way we did this was describe one method to compute features for an image, and then how you pass it to a machine learning model, and then you solve your downstream tasks like recognizing what's in the image, understanding how many humans there are, etc. In the second part of the talk, we spoke about how this is done today in the deep learning era, where you don't do anything manually, but instead you let a deep neural network compute your features for you, as well as classify it based on your downstream task. And the last thing we did last week was we showed you some fun results on the state of the field for 5 different tasks. So as Mark mentioned, the overwhelming majority of you said that you'd like to learn more about object detection, so we decided to deep dive into detection. So today we'll start with talking about what is detection, what data set do people train on, and how do you measure this. And then we'll talk about the same 2 things. How was this done back in the day, and how is this done today? Okay, so let's dive straight into object detection. So what is object detection? As we mentioned last time, object detection is the task of finding things in an image. And the way you denote what you found is you draw bounding boxes around them. So there are 3 objects in this image. There's a dog, there's a horse, and there's a person. And so you want to draw a bounding box around each one, and then you want to give it a label from some predefined vocabulary. So let's say that you're interested in finding objects from 100 classes. These labels are going to have to be one of your 100 classes. Object detection is one of the tasks in computer vision, which is a very wide range of applications that it's already being used in. For example, people are using object detection in smart refrigerators to figure out what's in your refrigerator and what you might need to buy. Of course, self-driving cars need to use object detection to know if there's a car in front of you, if there's a pedestrian crossing the street, etc. Over the years, a number of datasets have been proposed for object detection. One of the datasets that became very popular and is still one of the most important datasets that's used as a benchmark is called Microsoft COCO, Common Objects in Context. It has a very large number of images, 100,000 images, and for each of these images, people have labeled using crowdsourcing instances of all of these 80 categories whenever they occur in these images. Now, the first thing you might notice is that we spoke about ImageNet last time, which is used for classification, which had 1,000 categories. And object detection only has 80. And this 80 seems like a really small number. And there's a reason for this. And the reason is that it's more expensive to get object detection annotations in images. So for example, if you give it to a mechanical turker and just ask saying, is this a dog or a cat or a gorilla, you'll just, all they have to do is click a radio button. Whereas when they have to actually draw bounding boxes around every human being in the image and every fork that they're holding and every plate that they're eating from, things start getting very expensive. That's one of the reasons why you have object detection datasets with few categories. The other reason, of course, is that it's a more complicated task to train on. And so networks are starting to do a pretty good job at 80 categories, maybe 500 categories. They haven't yet got to the state where they can do well on, let's say, 10,000 categories. Okay, so before we go ahead, I thought it might be good to talk about if I had an object detector, how would I measure its performance? What is the metric used for this task? So let's say that I ran my object detector, I trained it in some way, and I ran it on a test image that it had never seen. And so let's say that I was interested for now in detecting all the people in this image. So I might detect a person here, and the system might draw a bounding box and say, this is with 0.9 probability on a scale of 0 to 1. It might detect another person here. It's not as confident about this person. It might also detect a person here, which is clearly a mistake, right? And if I look at the annotations for this image, what I find is I find 5 bounding boxes. I find 2 bounding boxes close by to what I had detected, and then I had 3 bounding boxes that I did not detect. And so this is what we call ground truth person boxes. And so how do I use these purple boxes and these orange boxes to compute a metric? So the first thing that we do to compute this metric is we take all of the detections and sort them by probability. So 0.9 being the highest, where I'm most confident, and I'm least confident about some detections that the model had made. And then the key thing in this metric is what we call intersection over union. And so what this is you take the detected bounding box, the proposed bounding box by the model, you take a ground truth bounding box, and you compute how much do they overlap divided by what's the area of the union of these two bounding boxes. And the higher the number, the closer the bounding boxes to each other. The lower the number, the further they are. And so this intersection over union is a good way to say, am I close to what a human annotator told me? And just as a visualization, if I go to 0.5 intersection over union, the bounding boxes already look pretty good. And of course, if you go to 0.9, they're almost perfect. And so metrics in object detection are reported at different values of IOU. Why is that? Sometimes your downstream task might only require you to say, well, I see some people in this image towards the left side, I see a car here, etc. But sometimes, such as in self-driving cars, it's very, very important for you to know exactly where the car is. And so based on your downstream task, you might choose a different IOU. Okay, so now I can compute this IOU for yes?
If you were running this annotation task, what kind of instruction would the annotator get as to what is the right bounding box?
The annotator is told to draw the smallest bounding box that covers all the pixels of the object. And so if my hand was like this, they would have to go all the way around. Okay, so now that I have a way to detect if one bounding box is correct or not, I can use this measure to say which of these bounding boxes are correct. And so everything that's correct is labeled a true positive. Everything that's incorrect is labeled a false positive, because the model said it was a positive, but this was in fact false. And now the next thing that we do is we take our sorted bounding boxes and we threshold it. So we say, well, I'm going to choose a threshold. Let's say I choose a threshold 0.2. So everything that the model said is less than 0.2 is stuff that I'm going to throw away. I'm only going to consider boxes that are above a certain probability threshold. And for these bounding boxes, I'm going to compute what we call precision and recall. I'm not going to go into too many details of this, except to say that precision measures of all the bounding boxes that I said were true, how many were in fact true. And so how precise was my machine learning model? Recall measures a different thing. It says, of all the bounding boxes that were actually present in the annotations, how many did I obtain? And so if I compute my precision and recall, I would ideally like both of these numbers to be very high.
Is recall usually at a particular IOU number?
Both are computed. So you first choose your IOU,
Choose your IOU and then compute
then find your true positives and false positives, and then use those to get precision and recall. Okay? And now the next thing we could do is, remember I chose an arbitrary threshold 0.2. What if I chose a different threshold? Well, I'm going to get a different number of bounding boxes, so I'm going to get a different precision and recall. And so as I vary my threshold, I'm going to get different points that I can plot on a precision recall axis, and this is known as the precision recall curve. And this is actually a very important curve because it allows us to look at how the machine learning model does at different recalls. So just a quick note about two extremes of this curve. Let's say I go to this part of the curve. At this part of the curve, I see that my precision is very high and my recall is very, very low. So what the model is doing here at this point of the PR curve is that it's saying, well, whenever I say that there is a human being, there is almost always a human being. But what's the downside? The downside is that I may not be able to detect all of the human beings. But when I do, it's very precise. If I go to the other extreme of the PR curve, it says, well, if there are n human beings in this image, I guarantee you that I'm going to get most of them. However, the downside is that I might also detect a lot of junk. So I might think the clock is a human being, I might think the laptop is a human being. I make a lot of mistakes, but I surely detect everyone. As you can imagine, based on a downstream task, you might want high recall or high precision. And so how do vision researchers decide which is the right metric to use? Well, the way they do that is they say, I'm going to take the average of the precision across all recalls. And so you want this curve to be towards the upper axis, which means you want to be doing well at all recalls. And this is the metric used in object detection. It's called average precision.
Question.
Yes?
What if one of the predicted bounding box intersects more than one true bounding box? So how do you compute IOU for those?
Well, the way they do that, I believe, is they just choose the one which is the higher one.
Okay.
Quick question. Could you use the IOU as just a parameter to the downstream task? Like, it's just a parameter to optimize over as part of your network in general.
I don't think people have directly optimized that as a parameter. What they have done is they've said, given a particular IOU, I can optimize my metric, but they haven't done that meta optimization.
I have a question.
Yes?
So IOU is just looking at how much intersection you have, right, versus union.
Yes.
But sometimes it may be crucial what part of the image you're looking at, like the trunk and face versus just the leg.
Yes.
So how does it account for what part of the image?
It does not. It considers every pixel on the detected person as equally important.
So are there other ways to look at, to give certain parts of the image more weight? Like when you're looking at applications like tagging a person in a photograph, then it may be crucial what part
Yes.
you're capturing.
Well, the two things I can think of is that if you had a systematic way of doing this or an automatic way of detecting this, let's say you knew that pixels towards the top are always more important than bottom. Like for human beings, it's okay to get the, it's much better to get the face and the body and not get the legs than the other way around. Then you could build this into your IOU computation. You could like weigh the area of intersection and the union by how high it was. But the other thing that you would really want to do is if you really want the face to be there, add face as a category. And so you say, well, what I need to make sure that I get all the faces.
Okay.
A last note on metric is that everything I told you was only for the person category, but you also want to detect dogs and cats and tigers and so on. And so the way the metric is computed is you take an average over all the categories. Okay, so now that we know what is object detection, what the dataset was, and how do you measure it, let's go into how you actually create a model to perform this task. So let's go back to the slide that we spoke about last week, where we had this image of a dog, and we want to classify if it was a dog or cat. And so the thing I told you was that we're going to compute some feature from this image. We're going to give it to a machine learning model, and then we're going to classify if it is a dog or a cat. So this is a two-class problem. Let's say I have an image here. This is an image of a little boy with a dog, and there's some trees in the background, and there's a car. Let's say I pass this through a very, very similar pipeline. If I computed a feature representation for the entire image and passed it through the model, I would want it to detect all the objects in the image. But this is not very well posed because it's not clear what's in this image. Is it a boy? Is it a dog? Is it a leash? Is it a car? Is it trees? And so this way of considering the image as an entire object and then assigning a single label clearly does not work for object detection. What you want to do is you want to zone in onto one part of the image and then treat this as a classification problem. And then you want to say, well, in this part of the image, it's a dog. And then if I zone into the boy, I want to say that part of the image is a boy. So how do we go from recognition to detection? Okay, so just a quick refresher on how features were computed. So let's say I went to a small part of the image. What I can do is I can crop this image, and so I can get a completely new image. I've just zoomed in to show you what the contents are. I can then divide this image into regions, and for each of the regions, I can do what I did previously for classification, which was compute some feature. And just as a reminder from last time, this feature computes, first of all, computes the gradient of this image. And what's gradient? Well, gradient reflects the magnitude and direction of the change of intensity of the pixels. So for example, if a pixel goes from light to dark, the gradient is in this direction. and the magnitude tells you how much the change is, and the direction tells you what direction the change is. And so if I take all of these gradients and compute a histogram of them, I get some feature vector that says, well, in this part of the image, how many gradients do I have that go straight up, horizontal, diagonal, etc. And so this is a nice one vector that I can compute that tells me a lot of information about this part of the image. Now what I can do is I can compute this vector for each of these 12 grid cells. 12 is an arbitrary number just for this visualization. It's often much larger. And I can concatenate all of these vectors to form a feature vector for the entire image. What does this feature vector represent? It says, well, how many vertical lines do I have here, here, here? How many horizontal lines do I have here, etc. And so for dog, it might say, well, on the left side, I have lots of vertical lines. On the right side, I have some mix. On the top, I have a horizontal line. On the very top, I have a vertical line. And so you can start seeing that it can start detecting things like, it can start representing things like legs and hands and face and tail and so on. And this feature vector, when given to my machine learning model, hopefully will tell me it's a dog. Okay, now let's say that I want to do this, but I don't know where the dog is. That's the whole point of object detection. I don't know where the boy is. And so what I need to do is I need to cut a bounding box, transfer this into a new image, run image classification. Then I need to move one pixel to the right and do the same thing again. So I need to do what is called sliding windows, where I need to take this sliding window, go to every pixel location, compute this, move it over, and so on. If an image is, let's say, 1,000 by 1,000, now I need to do on the order of 1,000,000 sliding windows. But that's only for computing something that has this aspect ratio. This car is not going to have a good feature if I use this aspect ratio, because there's a lot of noise. I'm also going to say grass and mud and water. And so what I need to do is I need to also take care of a box with a different aspect ratio and a different size. And then again, I need to slide it 1,000,000 times and so on. And so what people used to do, and this was exactly how we used to do it when I was in grad school, was have a large number of bounding boxes with different aspect ratios, slide each of them 1,000,000 times, run them through an image classifier, and finally do object detection. And that's why object detection was very, very, very slow. Okay, so clearly this is not scalable. So how can we do better? Let's say that I had this image. If I could compute some sort of segmentation of this image which says, hey, I think this is one entity, this is the second one, and so on. There are these 5 entities. I could then draw a bounding box around each one, crop that part of the image, and then give it to a classifier. So now from 1,000,000 or potentially 10,000,000 bounding boxes, we've gone down to just 5 bounding boxes. So this is the ideal case. If I knew that there's something here, I could pass just that something into an image classifier. So how do we do this? Clearly, we don't know how to do this, because if we knew how to do this, we already know there's an object there, and so that's most of the problem already solved. But we can do some approximation to it. What we can do is we can say, well, I'm just going to compute a segmentation of the image. I think we spoke about segmentation last time, and so segmentation is just grouping pixels together that have similar properties. And so you can see that the background is black here, and so all of this creates one segment. The woman's face may have a few segments for the eyes and the nose, etc. And so I'm going to just over-segment my image, and then every time there's a segment, I'm going to draw a bounding box around it, and I'm going to pass this to my object detector.
Is segmentation basically clustering?
Clustering of pixels. It takes 2 things into consideration, the color as well as the position. So this leads to a large number of candidate boxes. It's much fewer than 10 million, but it also doesn't give me the right result because I've over-segmented this image. So now I don't have a single segment that covers the woman or the television or the television stand. And so how do I go from this? Well, the way to do this is to do a segmentation hierarchy. So you take your over-segmented image, and then you have some sort of mechanism to start blending segments together. And the way you do it is you take 2 segments that are close by and not overlapping, but neighbors, and say, well, these kind of look similar, so I'm going to blend these 2 together. And then you do this recursively so that you form a sort of a tree structure. And then there are many heuristics that people used to use to decide how do I actually make these decisions. And once you have this tree structure, now you can say, well, I'm going to take the higher levels of this tree because these probably refer to objects, and I'm going to draw a bounding box around each one and then pass these to my featurizer and classifier. So now I couldn't do, in the cat's image, I told you that ideally we just have five bounding boxes. With this method called selective search, typically people can do about 2,000 bounding boxes and cover most objects in the scene. The reason it's 2,000 is that this is such a noisy procedure that it takes you down from 10 million, but there's still a lot of bounding boxes that clearly don't contain any objects in them. Okay, so how do I use selective search in object detection? What I do is I run selective search. I get, let's say, 2,000 what are called bounding box proposals. For each of these proposals, I compute features, run my classifier, and then classify into one of my 80 categories, which is dog or cat and so on. And this actually works pretty well, and this was how object detection was done a few years ago. So like I said, we've now gone from millions to thousands of bounding boxes. One thing that has been quite important when you do object detection is that you see when I do selective search, I might get lots of different segments based on how I compute my tree or how I merge segments together. I might get lots of bounding box proposals that are very close to each other. For example, what I might do is I might create one segmentation hierarchy using one mechanism and then have a different method to merge these segments, and so I can come up with lots of different ways of generating proposals. But there aren't 4 human beings in this image, there's just one. And there can't be 4 human beings with such close proximity. And so with that assumption, what we do is we do something called non-maximal suppression. So within a neighborhood, we take all the boxes, look at all the probabilities by the model, and choose the one with the highest probability. So this is very simple to implement, and it's very effective to reduce a lot of noise from our detections and land up with something close to the truth.
So we say the one with maximal probability. What's the probability?
It's the probability of it being a person as output by the model.
Is that determined from what it sees on the picture, or the position, its position relative to other boxes around it?
The probability is assigned independently of other boxes. But the non-maximal suppression takes all boxes into account and basically finds local peaks.
Okay.
So it says in this neighborhood, I see a lot of boxes, but this is the one with the highest probability, so I'm going to assume that this is the best bounding box.
All the boxes here are the same size, right? Otherwise you'd have to normalize for the number of pixels covered.
They don't have to be the same size, and typically in non-maximal suppression, people do not do this normalization.
So then you're more likely a priori for a bigger box is going to be more likely to contain the person than a smaller one.
Not necessarily, because if it depends on the aspect ratios of the boxes that were present in your training dataset. And so if the machine learning model has, like for dog, the boxes are more square, and so if I had this long box, it probably would have a low probability. Yes?
How do you get the same feature vector for different sizes of boxes?
How do I get the same feature vector? So
The length, the same length.
So in the pre-deep learning era, what you do is you divide whatever box you have into a grid cell, into a grid of the same size. And so even if it was this human being here, you would still divide it into 3 by 4. And so now you're computing for each grid cell, you're computing a histogram, which has a fixed number of bins. And so the length of your feature vector is the number of grid cells times the bins in your histogram.
So different sizes of boxes will still be divided into the same number of grids?
Yes.
Or you can do bag of words type of thing. So you have like a fixed number of words, and then you create a histogram based on that, and that's always has a fixed size.
Oops. Okay. So how do we go from what I just told you to doing object detection in the modern era with deep neural networks? So just as a reminder, the difference between how we did back in the day and today for image classification was, instead of computing these features manually, I passed it through a series of convolution layers, which finally told me if it was a dog or cat. And just as a reminder, the earlier part of the network would start computing things like edges and curves, and the later parts of the network would start capturing more higher level semantics, like what are the textures there, or what does it look like, or is there a tail, is there a face, etc. So if I went back to my image here, the way to do this was to just run selective search, get my, let's say, 2,000 proposals. For each of these images, each of those proposals, I would extract the image, warp it so that it's always the same size. Let's say it's 200 by 200 pixels, pass it through my neural network, and then classify. So this is how it's done. I mean, this is how the first neural networks were used to do object detection. All they did was they replaced the feature computation and the machine learning model with a CNN. And so now, if I took this image, I could just classify if it was a dog or cat. Another interesting thing that was done, which really helped results, was to say, well, I need to do two things. First, I need to determine if this orange box is a dog or a cat or a human being. The second thing I could do was that if the model already told me it is a human being, now can I sort of move this bounding box so that I can put it slightly better up around the pixels of the human being. So the first task is classification, which says what's in this box. The second task is regression, because what you're saying is, given that this is a human being, how many pixels do I need to move it up and to the left or to the right so that it's a better bounding box that looks like the bounding boxes in my training data. So the way this is done, without going into too many details, is you use the same network, but you have two loss functions. One that does classification, one that does regression, and you take a mixture of these two losses to do these in parallel. Okay, I'm going to pause here, and Rusbe will take over.
Okay, so yeah, just a bit of history that. So if you remember from last time, convolutional neural networks got very good results on ImageNet, but and as you see here, this is detection performance over the years for a particular data set, and so around like 2011, 2012, like the performance was almost constant. People like tried many different things, like let's use this type of feature, that type of feature, let's use Markov random fills and many different things, and they couldn't really improve the performance for 2 years or 3 years, and then 2012 they did CNNs for ImageNet, but people were still in denial. Like they said, oh, you can only do image classification, you cannot do detection, you cannot do segmentation, and so on. So this RCNN work that Ani just described was basically the very first work that showed that convolutional neural networks can be applied to other applications as well. So just a quick recap of what Ani said, and also note that these are all old papers, like 2015, 2016, and the current state of the art is kind of different from these, but they're inspired by those methods. So as Ani said, so we have input image, so we get a number of proposals, or they call it also region of interest. So and then they warp them to get boxes of the same size, and then they pass them through a convolutional neural network, and these SVMs are classifiers that tell you, okay, what type of object this is. Like, is it a cat? Is it a dog? Or and so on. So, and then this bounding box regression that Ani just talked about, like how to adjust the boxes so it fits the object. But there are a few problems with this. So it's very slow, because for each proposal you need to have a forward pass in the COMNet, so and that takes time, and you have like 2,000 different proposals, and so that will be slow. Another thing is that this classifier and bounding box regression was done afterwards. It was not trained with the rest of the network. So that was another issue that the RCNN model that Ani described had. And so people said, okay, so this was let's make this faster. So instead of doing forward pass for each proposal, let's compute features using convolutional neural networks, and then we do this type of pooling that for each proposal we only work on the feature that we computed once. Basically, you do forward pass once, and then you crop the regions that you like from that feature map. And then now you can also you will resize the boxes into the same size, and it goes through another some layers of neural networks, and you can do again you can find the object category, and also you can do bounding box regression that adjusts the box for you. So that was one tweak that made things faster and also help performance. But can we do better than this? So as Anya explained, that's the region proposals were obtained by selective search method, which was a separate procedure that took a long time to compute. But they said, okay, so instead let's have another neural network to predict the object proposals for us. So it has two routes, like one route that was like similar to before, and the other one was predicting object proposals using neural network instead of the selective search that we just talked about. So that also improved the performance a lot. So that was, again, you process the image once, and you don't you compute the proposals, and you compute the classifications and for each proposal. Then after this basically set of RCNN type of things, we had YOLO, which was developed locally, and the idea was to, so let's forget about object proposals, and let's directly regress the bounding boxes for the objects that we have bounding boxes for each object in the image. So I will explain the detection procedure, and then I will show you the network and tell you how it works. So they said, okay, so let's divide the image into a 7x7 grid. That's so we have 49 cells over the image, and then for each cell we do the following. Basically, for each cell they predict B boxes. X and Y, W and H are basically, X and Y are the center of the box, and W is the width, and H is the height of the box, and so for each cell that I showed, so they consider two boxes. So 2 is just an example. I think they use more boxes in the paper, but. So now, for example, for that cell that was here, so they consider these two boxes. So B is equal to 2, and then probability of object is the probability that the box contains an object. So they call it P object. So using this procedure for each cell, they compute two bounding boxes, and that with different aspect ratios and so on. So it covers the image. So then they predict the class for each cell and say, okay, so this class is dog, that class is that cell is dining table, and they assign a probability to each of the cells. For example, it's the probability of being dog is 0.8, the probability of being cat is 0.2, and the probability of being TV is almost 0. So then they can, for each of these boxes that I showed, they can compute the the probability of being a certain category. Like is it a dog box, or is it a bicycle box, and so on. So, and after thresholding and this non-maximal suppression that Ani explained, so they come up with a few set of boxes that contain the object. So, so this was the architecture of the network. So that so there's this input image, and in the final layer they get like 7 by 7, which is the 7 by 7 grid that I talked about, by 30 dimensions that I explained in the next slide, like what it is. And so they can directly get the boxes and the classes without a need for object proposals and so on. So, and that's basically how this last layer of convolutional neural network looks like. This 7 by 7 is the grid over the image, and then it has like 30 dimensions, like what's probability of object, what's x, what's y, the width and height, and also the probability for each category. Is it a bird? Is it a cat? And so on. So that's basically is the what that layers represent, and they try to learn all these things. And but as Oran always mentions, that all these things are basically human intelligence behind this, like how to like why we should do this and not doing that. So there is basically people this like where does this 7 by 7 come from? Why this feature should be like this? So all this the intuition from the designers. They are not that help improving the performance. So that's not something that's learned or anything. It's just fixed, and somebody came up with these numbers and this particular architecture. So in terms of performance comparison, so YOLO, the one, so it was not as accurate as faster RCNN, but it was like a little. The performance was a bit a little lower, but in terms of efficiency, it was like 3 times more efficient than faster RCNN. And also, we had this fast RCNN where the proposals came from the selective search method. So it was like 2 seconds per image, which is not really ideal. Like that's it's not really useful for any real-time application. And this was RCNN. The performance was much lower, and it took 20 seconds per image to process. And that's again, that was not very useful. So over the years, the performance improved, and also the speed improved. So yeah, that was basically it. So in case there's any questions.
Wait, can you just go back to your slide? So YOLO 9000, which you don't have time to go into, but I'm just curious, how much better is it?
Actually, I don't remember on top of my head, but yeah, I can tell you.
YOLO 9000 doesn't work better on the standard 80 categories that everyone tests on. What YOLO 9000 did was it showed you how you could detect such a large number of classes without having annotations for every class. And the way it did that is it said that, as I mentioned, detection data is very expensive to obtain. Classification data is easier to obtain. And so it said, detection data tells me how to localize things. Classification tells me how to recognize things. Can I fuse these datasets together?
Are the more recent, like YOLO 9000 or the other models that come out in the last year or so, are they taking a different approach, or are they refinements on the YOLO approach?
They're mostly refinements. So the work that I described are kind of the main ones, like, and then people got inspired by these, but there are like lots of tweaks and hacks and heuristics on top of those to improve the performance. So that's basically, these are the base models.
Is that what you guys are working on right now? Is it further refinements for the efforts you're doing?
That's one of our projects that basically that Ani is working on. Like that, also like another person in our group, Muhammad. Like so he's working on like how to make these things more efficient and cover more classes, because this data set was contained only 80 categories. Like now imagine you want to detect 1,000 categories. Like, how can you do that more efficiently?
Is there any work into like, my intuition is that some objects are easier to identify than others. Like a wheel is probably easier to locate and put a bounding box around than a car. Is there any way to say like, what's the probability, you have probably have the thing conditioned on the object, but can you condition that on like, hey, I already think of a really high confidence bounding box for a wheel. So it's probably this bounding box given that I know this thing over here is a wheel. Does it sort of use the other that way, or is it?
Yeah, so that requires like annotations for wheel,
Yeah.
first of all. So that's costly and hard to obtain. And but people have shown that for some of the older works that okay, so if I use like annotation for parts, the performance for object detection also that performance improves. So then that kind of makes a task easier, but it doesn't always help. Like for example, consider like cat leg, like it can be in any position. It might be harder than detecting the cat itself, or sometimes the hand in the image is very small, so detecting that is harder than detecting the person.
Thank you.
Are all these models pre-trained with ImageNet?
Yeah, exactly. So all of these are pre-trained using ImageNet. But they later showed if you don't pre-train with ImageNet and just use random initialization, you get a similar level of performance. But you need to wait longer to
So Ani spoke about how hard it is to get annotation for object detection, right? Like, do they use this idea of segmenting and proposing bounding boxes to make the annotation process easier?
So recently there are some methods that basically there is a machine learning model that assists humans to better annotate or annotate faster. But back in the old days, it was just mechanical Turk people, and so drew bounding boxes, and so that was how they got the annotations, at least for this COCO data set.
So there are two ways the machine learning model is helping today. One is, well, this is just bounding box. Now imagine you're doing segmentation where you want to draw every pixel.
Mm-hmm.
So there, people have showed that they can have a machine learning model. So the person just draws a bounding box first, and then the model tries to guess the segmentation, and then you just go and correct it.
Mm-hmm.
So that's obviously much faster.
Mm-hmm.
That's one way. The second way is to do a more holistic way. This is a very, very large data set called Open Images by Google, where they ran a machine learning model, and then it drew bounding boxes, and then they just had humans go and correct those labels.
Right.
But these data sets are biased because you can only make corrections, you can't add things.
Mm-hmm.
And so, as you can imagine, if the model never gets people wearing red dresses, then your data set will never have red dresses. So there's a big downside to using machine learning to get training data.
Don't most of the training regimes though alter colors and skews and perspectives and flips to sort of help compensate for that?
But there could be a systematic bias in your
Sure.
data,
Yeah,
which
okay.
they do not alter.
And are there like semi-supervised methods, like when you don't have all labels, and you know that if you have data for horse, you can probably use that to identify like donkeys or something.
Yeah.
That's
So Santosh had a paper last year where he said, if I know a lot of animals and I know some knowledge about how some unseen classes
yeah.
relate to these seen classes. So for example, a giraffe, giraffe is a bad idea, but let's say I have a horse annotated and I have the information that a zebra looks like a horse except it has stripes.
Right.
How can I transfer object detection using this knowledge? And the knowledge is present in some textual form.
Okay.
It's not present in visual form.
Yeah.
These methods are still at a very exploratory level. They work well it's sort of in a research setting, but going to this what is called zero-shot setting with no annotations for some categories doesn't work well if you want to deploy this in practice.
Sometimes it's hard to obtain annotations. For example, in medical applications, the annotators are doctors, and it's very expensive to ask them to annotate data for you. So there are, for example, like 5 images of something. So and you have to do inference, train your model just based on that, like 5 examples, and that's very hard. So one direction that people pursue is this few shot learning. Like, what should we do if we have just few examples of some category
What do you do?
for few shot? So we don't have any work in our group that handles few shot, right? So that
Yeah, we don't really work on that problem,
Yeah, yeah.
but people have been using meta learning. So what that means is that here humans are designing the methods of learning. So there you say, well, can I let an algorithm learn how to learn? And so you can now use this technique to say, well, how would I alter my, let's say, my neural network or my method of learning or my optimization if I had 1,000 data points, or if I had 10 data points, if I had 5 data points. And so these things start doing something better than random, but still few shot is still a very, very difficult problem. It's okay if the few shot categories are similar to ImageNet categories. Like, okay, I only have 5 examples of a dog, but I've seen 1,000 examples of cats. Then it's close by. If you go to the medical image setting with just 5 examples of tumors, it's very, very difficult.
And the reason I'm asking is for edge deployment of these technologies where you may have at this edge 2 or 3 or 4 or 5 or 10 samples of X, but it's the only location you got that, and you're not allowed to send those samples back up to a central training system.
I'm not most familiar with that work, but I think I can be pretty confident when I say that those things don't work very well. if you want to deploy them in practice.
For sure. Yeah. Okay.
Or we'll keep this video private, so your opinions make it out. Thank you all for the wonderful series. I'll get the videos and get them up on the internet. Incubator people, I'll have to figure out some way to get you this because you don't have access to your internet, but we can figure that out some way. Thank you all so much. This was wonderful. And enjoy CVPR next week. This is going to be like 4 times a month.